Thank you very much for introduction. I thank the organizers for giving me a chance of talk in this series of nice meeting. This time, the 12th anniversary edition of CAP meeting. And also, I thank the technical support by IHES Institute staffs for my online talk. So let me begin by my this. So the talk title is like this, and my talk corresponds to an archive paper. But this is actually already published a few years ago. But today I would like to talk about talk plus subsequent progresses. And these are joint work with Eiko and Hiroyuki Ogawa, also from University of Osaka. So let me start. Next. So these pictures are created by Maple software. So today's talk plan is divided 4 sections. And the first section, I explain what research curves and 3-body motions on this curve. This is a setting up of our main problem. And in the second section, I'd like to explain how we obtain a good topological representative for these motions. And in the third section, I explain geometric background, which is so-called shape sphere. It's larger sphere minus 3 points. And if time allows, I would like to talk about the motivation of our work from knot theory. So let me start the first section. So what is research curves? In this talk, I regard the complex numbers as just the Euclidean plane and 2 coordinates, real number and imaginary numbers. And then on this complex plane, we have parameterized curve. And here, M and N are individually horizontal angular frequency and vertical angular frequency represent, and A and B just the length of the box of this curve inside. And phi is just called phase difference. And if we move parameter phi, the curve continuously deformed. And t, it means the parameter of the curve, and we often regard as a timeline of this curve. Then, for example, these are research curve, and M and N represent the frequency of vertical and horizontal vertical. And if we move the phase difference psi, then the curve deformed continuously like this. So we have lots of such Lissajous curves depending on the frequency parameter. This is these are integer parameter, but phi is a continuous parameter deforming them. Okay. Then this we shall consider this curve on the complex plane, and these are just the repetition. But it is first observation is that this if you add one or shift the time to with adding one, then the same point is represented. So Lissajous curve is a closed curve. And the typical case is if A equal 2 and B equal 1, 2 means the length of this side, and 1 means the length of the vertical side. And minus 5 and 7 is just the frequency parameter. 5 and 7 is the number of number of mountains. And phi is in this case, it's a small deformation, but this graph is produced by these parameters. And we want to consider three-body motion on this curve. And if and this is so-called rock, paper, and scissors relations. And rock stronger than scissors, and the scissors stronger than paper, and paper stronger than rock. And they want to chase each other, or rather, in other words, they want to run away from the stronger people. And we put these three body put on the Lissajous curve, and if the stone is on the timeline t, then scissors is going t plus 1/3, and paper 1 minus third. But we can add any integer n, because the curve is has a period 1. So this kind of relationship occurs in the three bodies on the motion and on the Lissajous curve. And then it's, for example, this is a famous figure 8 three-body motion, and paper, rock, scissors chase each other or run away from each other in these relations. This is a 1 to frequency parameter. And this is a little bit complicated, but still the same policy produces such thing. And we often consider the triangle along this line. Triangle, the three vertices of these are connected by the lines. So then we regard this three-body motion as a so-called choreographic motion of a triangle on the Lissajous curve. And in the this is a Lissajous curve is rather just artificially considered mathematical viewpoint, but these are realized in celestial mechanics, and it is rather a famous result by Michael Montgomery. But I don't discuss this aspect today. Okay. And drawing the motion of 3 points along the timeline T, 0 to 1, produces a pure braid with 3 strands as long as the 3 bodies have no collisions. For example, the first figure 8 case is produces this, and if you move 3 points from the time to 0 to time 1, I like to read the braid from the top to bottom, so the vertical uh, uh, vertical coordinate is from the top to bottom. Yeah, and another one is looking like this. So if 3 bodies don't have collision, then they produce a braid of 3 strands. And if we restricting the timeline to 0 to 1/3, then it's 1/3 braid. So that it's the braid is not pure, but 3 bodies cyclically permuted. This then the aim of this talk is give a classification of the conjugacy classes of those Lissajous 3 braids, timeline 0 to 1/3. And we consider not not in the arching braid, but rather simpler. For simplicity, we consider braid group modulo center. This and we can give a good illustration of representatives in each class. So let me recall our aim. Give classification of the conjugacy classes of those Lissajous 3 braids and parameterized by 2 frequency parameter and 1 phase difference parameter, continuous parameter in braid group of 3 strands, but modulo center. Modulo center is equivalent to say modulo perspectives outside this system of 3 planets. Aim 2 is to give good illustration of a representative in each class. So I now compare two looking different 3-body motion in left-hand side and right-hand side. So, but one can produce such braids, 3 braids from the left one, and from the right one, this 3 braid. But if you observe closely, then one realize these 2 braids are deform each other. So our first task is classify. Conjugacy class means identify the topological equivalent classes. So we want to make the problem simpler in the collision-free case. This is a first assumption, but also some reasons of symmetry. We don't lose much information by restricting the frequency pair to those satisfying the coprime case. Coprime, if M and N has common divisor, then there is essentially nothing difference from the coprime case. And also, one can restrict the case m and n is 1 modulo 3. This is just if it this is not the case, you can change the reflection m to minus m or n or minus n. Then we can or essentially see the case these cases necessary and sufficient to look. And 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 collision-free condition, our first assumption is can be easily seen by this simple necessary and sufficient conditions, which means given m and n satisfying these frequencies hypothesis, then sometimes it could have a collision, but if phi is slightly changed, because phi is a continuous parameter, you can change the form slightly, the curve. Then we obtain collision-free three-body motions. So this makes sense. So, phi is not so a big problem for our classification. So this is the reason why we can essentially neglect the continuous parameter, phase parameter. If m and n horizontal and vertical frequencies fixed, then changing the phase difference phi amounts to our Lissajous three braids, not so different from each other, in the same conjugacy class or at most lying in the mirror reflected classes. So and the mirror means just the braid you can switch by mirror reflection, and algebraically the three braids is just the simple generators relation until standard presentation by Emil Archin, and mirror reflection is just left turn and right turn switching. So the changing the phase parameter doesn't make so much difference for this topological result, topological consequence. So this is a way of our strategy. So we have a frequency hypothesis like this, and also collision-free condition, but we can eliminate the effect of phase difference parameter, continuous parameter, by looking at the mirror union of conjugacy class and its mirror, the union of two, at most two conjugacy classes. Then we want to eliminate. We want to classify all Lissajous extended class of type Mn. So just this is notion depending only on the frequency pairs and doesn't depend on the phase parameter. Okay, so this is our target to study at the first level. Okay. Then we want to classify all Lissajous three-blade classes, but we don't need to consider all pairs, but we may reduce some good subsets of pairs, and which is like this. So this is just the frequency conditions, but we also can uh, impose this frequency is opposite signs, and the absolute value of m and n satisfy this mild inequalities. Then these rather restricted pairs exhaust all Lissajous three-blade classes, and moreover, if m and n is inside this calligraphic P, then different pair gives distinct classes. So this rather make our problem simpler than before. So we have such two three-body motion, and one was this one, and the other is this one. But these are these are previously I state these are the same, but same class, but this frequency 1 minus 2 is belongs to P, but minus 5 minus 8 is not belonging to this italic P set. So so in this viewpoint, 1 minus 2 is the nicer pairs, and the minus 5 minus 8 is somehow not necessary to think about. Okay, so this okay, so we want to we can consider we can restrict ourselves to consider these conjugacy classes, but m and n is belonging to the previous restricted pairs, standard pairs. And the goal is to the initial data MNP, so frequency pairs and phase difference, we associate a sequence, Frieze pattern of tadpole symbols, BDPQ. Tadpole is just animal before growing up frog. But BDPQ look like the symmetric symbol, symmetric four symbol, looking like tadpole. And then after establishing symbolic algorithm of this producing Frieze patterns, we can also define a three-blade in three-blade group modulo center. This is, in fact, this is PSL2Z, yeah, two by two matrices modulo signs. Okay, so first now I have to little bit to explain complicated procedure of the first how to produce M and N from M and N to BDPQ sequence. And so, for example, if m, n, and minus 5 and 7, this is satisfying the standard pair of P, then we first associate rational number, so-called slope, and positive integer, so-called levels. And in this case, we have 1 and 1. And then roughly we associate enhanced Christopher word associate this slope and level parameter, induced parameter. Then it is just the sequence of 0 and 1. Then we associate some tadpole symbol, Frieze pattern, in a simple rule. Then we interpret this Frieze pattern to 3 braids explicitly. So maybe we could skip, but just looking easier. So first we associate a given standard pair M and N in P. We associate positive number integer n, level n, and positive rational number called slope xi. Then first, from the slope xi, we can produce the so-called Christopher word of 0-1 sequence as a 0-1 sequence, which I will explain briefly in the next sheet. Then we repeat Christopher word twice, double the Christopher word, and then associate level n, we enhance this doubled Christopher word in the certain rule. So 0 is going to one of these 4 symbols, 1 is going to one of these 4 symbols, and if m is positive, then begin by P, and if m is negative, then begin by Q. Then every word from PQ sequence should be adjacent to a word of DB symbol, and QP symbol have to adjacent. These are kind of algorithm how to associate from MN to BDPQ tadpole symbols. Then finally, each PQBD is associated to these explicit 3 braids. Then we obtain the Lissajous representative of Lissajous class for the pair M and N. The Christopher word, what was Christopher word? Just it was simple. This is a slope P Q over P. Then we obtain the 0-1 symbol just considering the P times Q rectangle and put draw the diagonal of slope Q over P. Then closest lattice path to the diagonal in this way, and read 0 and 1 just in these steps. Then, for example, if slope is 3 over 5, then looking like this, we obtain the Christopher word 001, 001, 01. Then we obtain from this standard frequency pairs, we first consider the, okay, so level. What is level? we divide the one to semi-closed interval and decompose this interval by the decreasing sequence of rationals, 3n minus 1 over 3n minus 2. Then we decompose interval 2, interval 1, 1 to 2 by this sequence, decreasing sequence. Then we find where absolute value of n over m is contained in this decomposition, which decompose the smaller interval. Then this is how we determine the level n. And then if we once determine the level, then m and m minus n over 3 has a unique solution of positive integer by these equations, simultaneous equations. Then we obtain the slope q over p xi with this satisfying this condition. And it is not difficult to show this standard frequency pairs is one-to-one correspondence with the pair of positive integer and positive rational numbers. So these are both of the P and L is the countably many sets. So not difficult to imagine the bijection between this set and this set. Then step 3 is just I repeated the previous thing. So if we obtain the Christopher word of slope xi, and then repeat it twice, and then enhance 0 and 1 by this one of these PDPQ words, and this is the initial condition, and also the alternating condition in this way. Then we obtain 3 braid. For example, if the simplest one is m and n is 1 minus 2, then slope is 0 and the level is 1. Then enhanced Christopher word is just 0, 0. And then 0 is going to P, and next 0 is going to D, this one, yeah. Then the P and D is switched replaced by this braids. And another example, minus 5 and 7 case. This is, in this case, slope is 1 and the level is 1, and the 0101 is enhanced Christopher word, and associated tadpole symbol is like this. Okay, so I have to go faster. So M and N, more and more complicated, but level 2 and slope 1 over 4 and enhanced 1 is like this, and minus 17 and 25, and then level n equal 1, and slope is 3 over 5, and so on. Then we compare these 2 examples, and the first example is frequency pairs odd number and even number. And the second example, both frequency number is odd numbers. So then if the first case, both Mn and PQ are even, And then this BDPQ sequence is first half and the second half is not the same. It's rather mirror um, uh, mirror associate each mirror to each other. But in the odd case, we observe both these two parts. Half and second half is just a repetition of the same sequence. So even case, half and its mirror appears. And odd case, both odd case, half and half are repeated twice. So geometric background, I just want to translate this choreographical dance of triangles. We want to translate this motion into the Lissajous curve, along the Lissajous curve into a closed curve on the triangle moduli space, so-called configuration space of 3 points on the complex plane. Then the Lissajous triangles forms a closed curve, giving an element of pi 1 fundamental group of this configuration space divided by the symmetry of 3 punctures. And this is just an algebraic group of 3 strands. And we consider the shape function from configuration space ABC, the triple of ABC, to sphere minus 3 point. It's regarded as a projective line, complex projective line minus 3.1 omega square. Omega is a root of third root of unity. And this is this shape function is defined as a quotient of finite Fourier transform of these 3 vertices of a triangle. Then we obtain the curve on this sphere minus 3 point, and we want to trace the image of these points on this sphere. So sphere minus 3 points is we may regard easily as a sphere like this. And then, but we want stereographic projection of this space by from the North Pole, and the South Pole is going to infinity, and the equator is just the unit circle on the complex plane. Then, okay, so this is a on this plane we have orbit of the shape functions of the Lissajous motion, and then we associate each moving of this south and north hemisphere, and associate BDPQ in this way, associate the symbol like this. Okay. So we have so braid group and modulo center. We have 2x2 matrices, and this association BDPQ in the previous sheet is going to these 2x2 matrices, and which generates an indexed subgroup of PSI to Z. It is a free product of 3 cyclic generated by these. And how to translate the behavior of the orbit in braid words is we just want to consider deformation of the A is much bigger than B, then just this deformation is just going to this continuous deformation. So the braid type is the same as any A and B. Then in this deformation, these are almost like one. And these are just moving, represent the moving on the equators. So, and this is some small figure eight vibration of this orbit. So, if A is much bigger than B, then it looks like a simple behavior surrounding equator, but a little bit fluctuate on over it. So this is the case of m equal 1 and n equal minus 2. And then this is produce this triangle moving. And in this case, also more complicated, but on the orbit is like this. And the old paper by Caroline Frieze and also Caroline Frieze relates this geodesic on Poincare upper half plane and cutting sequence of Farey tessellation and continued fraction expansion. And also Boca Merriman considered the checkered version of this of their work. So in this case, we have such related objects like this. So this is moving on the shape sphere, and then we make uniformization of this three punctured sphere on this Poincare upper half plane. Then the north hemisphere and the south hemisphere is going to ideal triangles on the Poincare space, and then this our moving of the Lissajous orbit may be realized as a geodesic on this plane, and then if we expand this ending point as a odd term continuous continued fractions, then this also explained somehow BDPQ words. Okay. And so frequency, we obtain north sphere and south sphere, and going to this orbit, cutting this way. Then we cut right, left, right, 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 left, right, 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 left, right, 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 left, 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 and then we obtain such sequence like this. Okay, so this is a case of that. So in this case, minus 11 and 16 case, and the phase parameter are 13 pi over 11, and time is 0 to 1/3. Then the triangle dances like this, but also the orbit on the three punctured sphere looking like this. And if we develop it on the stereographic projection, it's moving like this. And oh, sorry. So this is the case. And we observe in the type 1 case, MN even case, both even case, then phase difference 0 stays collision free. Then the Christopher word is half plus mirror shape. Then we can shift it a doubly palindromic sequence, and which is intensively studied in a first paper. And in the odd case, this case, phi equals 0 has a collision, so we have to work another way. Then this is in preparation as a joint paper. Okay, so now the time is almost over, but maybe within 3 minutes, I want to mention the motivating problem, the knots obtained by closing Lissajous braids, so-called special case of Lissajous toric knots. And you can go to Google. There are two different Lissajous knots. One is usual Lissajous knot, and the second one is Lissajous toric knot, which is closely related to our work. And these were knots were studied by Christoph Lam and Sore Bill paper many years ago. And these two different classes exist. And in the case of this one, we have the BDPQ word is like this, and we close these two knots by connecting the corresponding string. Then these strongly gives strongly positive amplicality knot. And sorry. Sorry. This is one. And if we double this braid and closing, using closing, then we can obtain the so-called figure 8 knot. So, but in the paper by Soreville, they considered another thing, another Lissajous toric knot. And I could resolve their example by deforming. Then we obtain this. Their example cannot cannot be produced by type 1, and we needed the type 2 Lissajous braids. So this motivated by other study general phase differences case. Okay. So this was the paper is under preparation. Okay, so thank you very much for attention.
Okay, thank you. Now is the time for questions and comments, please.
Why 3 punctures? Is it?
Can you speak loudly?
Can you hear me?
I could hear, yeah.
Why 3 punctures? Is it because of 3 braids? Can you do 4 punctures on the sphere? 5?
Yes. Yeah. So 3 punctures is Yeah, as you say, it's simplest non-trivial case, and of course we should consider four puncture and so on, and also four braids. And Lissajous toric knot considered by their paper is actually n-body motions on the Lissajous curves. So we should study more points. Yes, it's a good question. Yes.
How difficult do you think it will become, or it's not so difficult if you want to go?
Difficulty. So moduli space is, in our case, moduli space is just a surface or complex line. But if you increase the number of points, then the modular space is more has more dimensions and some more skill with the higher dimensional variety. So we still don't enter this level of studies, researches.
Thank you.
Okay, Pierre-Vincent?
I have a question. What is type 1 Lissajous?
Why?
Type 1, what is it exactly?
Yeah.
Type 1. What is type 1 Lissajous knot?
What is type 1?
Type 1. Type 1 is a case of we start from t equals 0 and the time phase difference equals 0. This is the type 1. Or more explicitly, we go to, for example, this first this case, this standard after standard reduction, we consider this case. Then actually, if m and n is both odd, is type 2. And one of them is even, then type 1. So it's almost half and half, type 1 and type 2.
Okay, so now the time for last comment or question. Gerard?
Yes. Could you return to your slide, which looks like origami with, with triangles and green and
origami?
Yes, it looks like it. Looks like. I will say to you.
Sorry.
Yes.
This one?
No. Go on.
Like this one?
After. Yes, after.
Okay.
Yes.
This one?
Yes. I could not catch, but
yes. So
maybe.
We had such 3 sphere minus 3 points, and 3 points is on the this red equator. So we have 3 points here, 1 and omega square. And we divide this sphere as into the north hemisphere and south hemisphere, but the vertices is this puncture, 3 punctures. So it's not like a triangle, but in the sphere geometry, it's north hemisphere and south hemisphere, and 3 vertices is 1 omega square and 1 omega square. So this means then we have orbits of Lissajous motions. Then how to cut this this sphere can be read off from the way how okay, so the orbit cut north hemisphere this way or that way, and south. Then after that, south hemisphere this way or that way. Seeing the punctures on the left side or right side. So then all of this information can be included in this BDPQ words. This is a.
Thank you.
Okay, thank you very much. We thank the speaker and the.
Thank you very much.